Hello, Assalamualaikum warahmatullahi wabarakatuh. I'm FADILLA AZELYA from 6B, and in this video, I would like explain about confidence intervals and statistical significance. Okay, the knowledge and skills you need to explore, describe, and conduct routine analysis of a quantitative dataset. The data you collect could relate to specific aspect in that something on your research and your content just to analyze those data in relation to a particular issue or set of issues you're interested in. So, confidence intervals, we will start with the notion of confidence interval. There are actually two main types of confidence intervals that we would generally deal with, one relating to the mean that we would calculate for a scale variable and the other relating to a percentage that we would calculate for a categorical variable, i.e. a nominal or ordinal variable. We will look at each in turn. Confidence intervals for means to gain an intuitive feel for what it is all about. Alternatively, you may have data for all schools in your own school board or local education authority area and would like to explore and analyze key performance indicators across these schools. Moreover, if you have access to data gathered as part of a census, i.e., a survey of all schools or a all survey of all members of given population, then again you already have the knowledge and skills necessary to conduct routine analysis of those data. We will use the youth cohorts.sav dataset and focus specifically on the scale variable GSAPs that represent each young person's GCSI score. This variable was introduced in the previous chapters and represents a measure of a young person's level of attainment in public examination at the end of their final year of compulsory schooling. It's worth warning you at this stage that this is the chapter that some of you might find most difficult to follow initially. This is not because we're about to dive into complex and nasty mathematical formula. In fact, have a quick look ahead. You will be relieved to know that is still all in words. To begin with, open up the dataset and for the purposes of this exercise, do not apply the weighting variable as one weight. Use the analyze descriptive statistic explore produced to get an overall feel for this variable. The partial results of these are shown in output 5.1. From this you will see that the unweighted variable ranges from 0 to 117 points with a mean of 49.29, and standard deviation of 19.35. If you have not to these features, then you have most likely applied the weighting variable, so reset with cases and try again. You will also see form the system and leave display that is produced by default in SPSS, that the variable largely resembles a normal distribution except for the floor effect noticeable by a slight bunching of cases at 0. Okay, this is the descriptives of output 5.1. To do this, choose Data, select Access. This opens up the Select Cases window you have already been introduced to in the previous chapter as shown in Figure 5.1. This time, however, choose the third option down, Random Sample of Cases, and click on the Sample button. This opens up the additional window, also shown in Figure 5.1. Here we will specify that we want SPSS to randomly select a sample of 200 cases from the first 13,201 cases, i.e., the entire dataset. If you have a student version of SPSS, then select 50 from the first 1,450. Do this as shown and click Continue to return to the main window. Ensure that the Filter Out Unselected Cases option is chosen and then click OK to finish. You should notice that most cases have been deselected and that the Filter On label has appeared. See Figure 3.3, indicating that only the random sample of 200 cases selected is now active. Once you have done this, use the Analyze Descriptive Statistic to descriptive procedure to calculate the mean for your sample of 200 cases. And this is Figure 3.3 and the Figure 5.1. So, in the Figure 3.3 main SPSS window indicating that the Select Cases procedure is being used. See the arrows. Once Select Cases has been defined, the Filter On label will appear below and those cases that do not fall into the subsample selected will be crossed out as indicated here to the left. And next, Figure 5.1, selecting a random subsample of case in SPSS. The first, select the option Random Sample of Cases here. This opens the window below. Second, select exactly and set it so that 200 cases are selected from the first 13,201 cases as shown, or 50 from 1,450 if you're using a student version of SPSS. Click Continue to return to main window. Third, Make sure that filter unselected cases is chosen, then click OK to finish. What you should find is that the mean is pretty close to the mean we calculated for the population as a whole, but it's likely to be slightly different from it. Now, don't close the SPSS output window, but just minimize it instead. Return to the main dataset and open up the Select Cases window again. Data to Select Cases. Click on the Reset button to reset Select Cases and to go through the same procedure again of selecting another random sample of 200 cases from the entire dataset, i.e. the first 13,201 cases as explained above. See figure 5.1. Repeat the procedure a few times so that you can compare the means of 5 or 6 different examples. Hopefully, you can see that the means from each your small samples are actually fairly good approximation to the actual mean for the population as a whole, and that they just tend to vary slightly within the range of about 2 or 3 points, either above or below the actual population mean. Doing this exact procedure 20 times, I come up with the 20 example means shown in table 5.1. And this is the table 5.1. The means of 20 example selected from a population of 13,201 cases where the population means is 49.29. What we can see from this is that this random sampling procedure tends to produce unbiased estimates of the population mean. In other words, there is no systematic bias of involved, but rather the means of examples tend to be randomly secreted either side of the true population means. However, what we do see for each sample means in a certain degree of sampling error, in that none of the example means is precisely the same as the true population means, because these are random examples. This is to be expected and is simply a byproduct of the vagaries of random selection. Sometimes our example of 200 cases will tend to include a slightly higher proportion of pupils with lower GCSI point score than one would expect, and hence we get a sample mean slightly below the population mean, and on other occasion we will get a sample with a slightly higher proportion of pupils with higher GSCE point scores that would be expected, and in this case our sample mean will be slightly above the population mean. And this is the figure 5.2. Distribution of the means of 20 random samples selected from a population of 13,201 cases with a population mean of 49.29. A histogram displaying these 20 samples mean we can see that they tend to be normally distributed as shown in figure 5.2. In fact, if we continued with this exercise and created more and more examples, then what we would see is that the more samples we create and calculate the means for, the more this histogram would come to approximate to a normal distribution. Moreover, the average of these 20 example means can be seen to be 49.50, which is getting pretty close to the population means of 49.29. Now let us use the analyze, descriptive, statistic, and explore. Produce to explore the first sample, you should get the output shown in output 5.2 as can be seen later. The mean for this sample is 47.67 and the standard error is estimated from the data as 1.34. What we can now do, in line with the above condition discussion, is to take these figures to make the following points. There is a 68% chance that the true population mean lies within the range of one standard error of the sample means. There is a 95% chance that the true population means is within just under two standard error of the sample mean. This is mean this a 95% chance that the population means is contained with the boundaries 47.67. Finally, there is a 99% chance that the true population means is within 2.58 standard errors of the sample mean. What we have actually constructed here then are confidence intervals. They provide us with some sense of the margins of error associated with any summary statistic, in this case the mean of a sample. Okay, this is the descriptive output from 5.2. Okay, the first standard error for the means an estimate of what the standard deviation of the distribution of sampling means would be. The second, boundaries for the 95% confidence interval. You can ask SPSS to calculate the boundaries for any confidence intervals by clicking on the statistic button in the Explore window. Okay, that's it. Please forgive my mistake. Thank you for your attention. Thank you for watching. Assalamualaikum warahmatullahi wabarakatuh.